I'm happy to be here to talk a little bit about the need for exascale computing for the fusion community. So we are definitely one, and have been for decades, actually one of the drivers of high-performance computing, whatever that meant in a particular point of time. And I want to start by giving you a very quick introduction to fusion in case you're not familiar with it yet, and then I'll go to the exascale part. So fusion is often mentioned in the media. There's high hopes for fusion, but there's also big challenges, and we hope that high-performance computing can play a key role in addressing some of these open questions. The basic idea is simple. For about 100 years or so, we have known how the sun shines, namely by the fusion of protons to helium. In this process, mass gets lost, so to say, and is transferred to energy according to Einstein's famous formula. And the idea is to take a process like this to produce carbon-free energy for the 21st century and well beyond. On Earth, we do not intend to use exactly the same process because one of the stages involves the weak interaction, which has a very low cross-section. So instead, this one is better. It's actually by far the best on Earth. So we take deuterium and tritium, two heavy versions of hydrogen. They fuse to produce helium and a neutron. The helium will be used to heat our system, the plasma, I'm going to discuss in a minute. And the neutron leaves our device, hits the wall, heats the wall up, and from there on it's conventional technology. Basically, a hot wall has to be cooled, and you produce electricity in stages. The downside is, in order to make this happen, we need a gas with a temperature of about 100 million degrees, which sounds enormous, but actually, as I talk now, we constantly produce these temperatures on Earth. So that's not the big problem. We have other problems. I'm going to address some of those in a minute. So we are dealing with a fully ionized gas, which we call a plasma. And actually, most of the visible universe is in a plasma state, 99-point-something%. So we consider it on Earth to be an exotic state of matter, but really, on the big scale of things, it's a very natural state of matter. So on the left, you see the constituents of our plasma. We have ions, potentially of various sorts, and we have electrons, and they spiral about magnetic field lines. And we use this as the basic idea. If we manage to form a magnetic cage with magnetic field lines that are kind of localized in some way, for instance, if magnetic field lines form nested toroidal surfaces, like in a donut or like other toroidal geometry, then these charged particles will spiral about the field lines and basically remain on these magnetic surfaces. That is the basic idea, and it's correct to lowest order, as we say in physics, but there is an effect which originally was not on the map, but we had to find out that we have turbulent processes which mix the plasma, so to say, and the temperature difference of about 100 million degrees between the core and the wall, which is only maybe 1, 2, 3 meters away, induces these turbulent fluxes, and the plasma is lost at a much higher rate than originally anticipated. This was already mentioned this morning briefly. So this is our next crucial step in fusion research called ITER. The goal is to produce what we call a burning plasma. So this is a self-heated plasma and 0.5 gigawatt of fusion power. It has a very nice website, which is mentioned here if you are interested in the project. And I want to know in passing that the 7 ITER partners correspond to more than half of the world's population. So there's a lot of interest all over the world in this project. This is part of the construction site as of now. So there's a lot going on this site in Cadarache near Aix-en-Provence. And the main reason for investing in such a big project and taking all the challenges is that the resources for fusion are practically unlimited. For instance, if you take the deuterium that's contained in one bathtub full of water and the lithium in one battery of a laptop, that together can give you enough deuterium and tritium to produce the energy for an entire family for half a century. So that's the incentive, and that's why we embark on this complicated journey. So that's the background part. Now I want to say a few words about extreme computing. There are at least 3 key physics challenges on the way to fusion. There's, on top of that, there's technological challenges of various sort, including materials. But these are the 3 that I would consider the most crucial on the physics side. So the first is, which I already indicated, we have turbulent transport in the core. So everyone who drinks coffee knows it's a smart idea. If you put your milk in the coffee and you want it to disperse quickly, you create turbulence with a spoon, because turbulence mixes fast and well and thorough. Here it's detrimental, but we cannot avoid it, unfortunately, although we are looking for ways to control it at least to some degree. So the hot plasma from the core is expelled, and this defines what we call the energy confinement time. But this energy confinement time has to exceed a certain threshold for the plasma to be self-heated or burning. So that's a critical question. A second big question is what we call large-scale instabilities, which are described by a variant of a hydrodynamic model. So you all know fluid theory, hydrodynamics, and there is a version called magnetohydrodynamics, which applies to plasmas and liquid metals. And such a theory can be used to determine under which circumstances does such a plasma become unstable on large scales. And basically the whole discharge falls apart and the experiment is ended. So that's something you have to keep in mind. And the third crucial question is the interaction between the plasma and the wall. Because that is bad for the plasma, which will be cooled. It's also bad for the wall because it will be destroyed potentially in a much shorter amount of time than you wish for. So in the remainder of this talk, I will emphasize the turbulent transport question, but keep in mind that there's more. In particular, there's materials-oriented questions which have a lot of overlap with what we've heard previously from other speakers. So as you can imagine, we are dealing with a wide range of space and time scales. So in terms of space scales, we cover maybe 7, 8 orders of magnitude, and in terms of time scales, it's even worse. So it's completely hopeless to think that we can come up with a first principles-based model that covers everything. So the challenges here are very comparable to those in material science, for instance. You know, you cannot do a quantum mechanical model that describes the deterioration of your material, let's say on the timescale of 10 years. That's not the goal. So you have to be smarter and you have to find ways to model your individual processes in smart ways. On the lower left, you see also, again, space and time scales and how different important processes like turbulent transport or these large-scale MHD instabilities or wave feeding and other things, how they are situated in these 2D map. I would say the key theme as of now in our community is towards more and more integration. So in the past, we had groups focusing on individual aspects. Like one group worked a lot on turbulent transport, another group worked on the large-scale instabilities, a third group had its focus more on the boundary and so forth. But now we get to the point where we see that in order to make valid predictions about the behavior of such plasmas and the performance of devices like ITER, we have to make sure that we come to an integrated view of the whole plasma. And that means that all of the topics that are mentioned on the box or on this ellipse on the upper left, they talk to each other as we see more and more. And they talk to each other in ways that are nonlinear, so you cannot easily cook up a simple model. And it involves many space and time scales. So this is our challenge, basically. We have to get from a more pillar-oriented approach where we isolate individual aspects to a more integrated point of view. And this is done by means of applied math and computer science as helpers. And we also have close relationships to plasma astrophysics and complex systems research. So this is kind of the environment. This slide gives you an overview of our past trajectory and looking a little bit into the future. So I would say roughly in the 70s, 80s, we started to do simulations that were very idealized. The geometry was idealized. The physics was significantly simplified. Yet, we get a first glimpse into the turbulent processes that determine this energy confinement time. Several years later, in the teraflop era, we were able to spice up the physics contents. Now the simulations were much more realistic. The geometry was realistic. And we were able to start doing first comparisons with experiments. In the petaflop era now, we are doing pretty comprehensive simulations already. And we are consistently, basically on a daily basis, comparing simulations with experiments. And usually, maybe after some trial and error and some back and forth, we get pretty good agreement in most cases. So that is considered a big step forward. So we are now in touch with the measurements. And we think that the next step is, after we have validated our tools, that we can actually go from a post-diction mode to a prediction mode, so that we can actually guide the experiments in certain ways to make sure that they get the most out of an individual experiment like ITER. Currently, we are working on a more complete picture, as you can see here. So two codes, one that covers the center of the plasma, another one that covers the boundary, are about to be coupled to then cover the entire plasma from the wall to the very center. And this is supposed to act as a backbone for future developments where other physics effects are coupled in, and then you have something like a virtual tokamak. So that's the dream. A virtual plasma experiment that can be used to guide either experiments or even the development of future devices that don't even exist yet, even in theory.
I'm just curious to know, when you say that now you are in the position to compare with the experiment, these are experiments that you do in the fusion phase or before?
No, as of today, there is no experiment that can get to what we call this burning plasma state, where a significant, let's say at least half of the heating power comes from these fusion alpha particles. Today, we have reached this twice in TFDR experiment at Princeton and at the JET experiment near Oxford in the UK in the 90s. And we are targeting to repeat such experiments at JET and then go a big step forward with ITER towards this burning plasma. So we have limited experience in this regard. What the experiments we do on a daily basis as of now are not in that regime. They're not of the burning plasma type, so to say.
But the stabilities are already there?
Yes, absolutely. And they will be there in ITER and beyond. So this is kind of our trajectory. So this sounds extremely ambitious, maybe impossible if you look at it alone. But if you actually put it together with where we came from over the last 20, 30 years, I would say it's certainly extremely challenging, but not impossible. So this is a workflow diagram that has been set up in Europe, called the European Transport Simulator. And each box represents a certain type of physics. For instance, here is a turbulence module. So that's basically what I showed you on the previous slides. The simulations that will feed into this, but then you have other things. You have large-scale MHD, you have heating and other things, and this will all be coupled in various ways to come up with what we think is like a virtual tokamak. So these simulations use high-performance computing. Actually, fusion has been a driver ever since the 60s. The first big computing center in the US for non-military purposes was NERSC, and it's in California, and the driver was fusion. Originally it was only fusion. Later on, the portfolio was greatly expanded. So this is a scaling, what we call strong scaling, so keeping the problem size fixed, but increasing the number of cores on Titan, which is currently, I think, the third largest computer in the world. We go to about 90% of the machine even using the GPUs. So that's what we can use, but unfortunately that's also what we have to use in many cases to make these predictions. So this is taken from a code called Gene, which was developed in my group, but there's also in Europe 2 other codes that are very much pushing in this direction. ORB5, developed mainly in Lausanne, and Gisela, developed in France, and also part of the project we're discussing today. So obviously, this is not just about brute force. There is a significant role of applied math and computer science, and I want to give you just one example to highlight this fact that it's not just getting the largest computer and then throwing your code on this computer and seeing what it can do for you, but you also have to be very smart about how you do the simulations and the kind of reductions you can maybe do. So again, just one example is shown here. Maybe you are familiar with the notion of sparse grids. So the idea is, especially in higher dimensions, that the number of grid points, let's say you have 10 grid points in one dimension. And these simulations I showed you with turbulence, they are actually kinetic simulations, not fluid simulations, because these hot plasmas are virtually collisionless. So fluid theories cannot be used. You have to use kinetic theories, which in principle are 6-dimensional, but we can get rid of 1 dimension. That has to do with the strong magnetic field in the background. So we are left with a 5-dimensional problem. So, you know, whatever you have, n to the 5 becomes a very large number, of course. But we can use a technique called sparse grid techniques, where we actually thin out the grid in various ways, and we solve the problem on all of these grids, and then do a linear combination of the results to get an approximation for the complete problem. So this is an example. This is a simulation, whatever it is, on a full grid. These are 7 simulations on sparse grids, and you can see that each of them looks totally different from this. But if you combine those in the correct way, you get the picture on the lower left, which is remarkably similar to the one on the lower right. In other words, you can replace the full-blown problem on a 5-dimensional, well-resolved grid by simulations on sparse grids if you do it properly. Now, this has at least 2 big advantages. The first one is you introduce a new level of parallelism. You know, you can solve these problems completely independently of each other. That's beautiful, although you have to take care of load balancing, obviously. The second big advantage is that this is a way of algorithmically ensuring fault tolerance. Let's say you run on a huge computer. The chance of this simulation not surviving, let's say, 24 hours without a node failure is very large, and will be even larger on exascale machines. So what do you do? The naive approach would be you write out your data, but this can take a long time. So maybe there are better or alternative approaches, and this is one of them. Let's say we're running these 5 incarnations of our sparse grids, and a node fails, which means that we cannot get the answer from one of those. Then you can do 2 things. Either you rerun just this case, which is much cheaper than rerunning the whole thing, the well-resolved one, or you just ignore this case and you modify your linear combination to get an approximation for the solution that you would have with all 5 implemented. And that may be good enough to continue the simulation. So you can keep going, although your computer technically crashed. So that's just, again, to give you a flavor of the kind of applied math computer science problems that we're working on to ensure that we can do these extreme scale simulations. And in my final part, I want to give you 2 examples, basically, of discovery science that has been done with the help of extreme computing, where we have first observed a certain phenomenon on the computer, and later on we have verified its existence in an actual experiment. So about 15, 20 years ago, everyone thought that the relevant scales for the turbulent transport are from maybe a fraction of the system size down to what we call the ion gyroradius. So that's the diameter of an ion spiraling about these magnetic field lines, which could be a few millimeters maybe. So we're going from, let's say, a meter to a millimeter. That's bad enough in terms of spatial scales. But we knew for a long time that, so this is the linear growth rate as a function of wave number. When you go to the upper right, that means these instabilities which drive the turbulence live at smaller space-time scales. So we knew that there were these electron temperature gradient or ETG modes, but everyone thought, based on back-of-the-envelope calculations, that they're not important. But around 2000, there were some simulations which I was involved in, where we found that actually ETG modes can be important, which means that we have to extend our scales down to the electron gyroradius scale, which is 60 times smaller than the ion gyroradius scale, which people considered before. So this is an example. This is such a simulation where you see large-scale structures on ion scales drifting down, but there's small stuff here. It sounds or looks like noise, but it's actually turbulence on these much finer scales, which were neglected until 15 years ago. And on the left, you can see where the turbulent transport is done. This peak is on the ion scales that were always on people's map, but there's a second peak here for the electron heat flux on much smaller scales, and these were neglected in the past, and now we know we need to include them. So this was the prediction about 2000, 2002, and I will not show you now, but I can tell you that several years later, people found ample evidence in various experiments that this transport channel is actually active. It needs to be considered and existing in future experiments. And this is the first simulation ever to be done for an entire plasma, down not to the ion scale, but to the electron gyroradius scale. So these, this is just a blow up of this small section, and you can see here these points that look almost like noise again, are actually turbulent transport, because if we plot the transport spectrum, there's something at ion scales, but there's a lot at electron scales. And this was only possible because it was a relatively small device. It was the TCV tokamak in Lausanne in Switzerland. This was a 10 million core hour simulation, and the goal in the future will be to do similar simulations for larger experiments, ultimately for ITER. A second example in this category is a stellarator. So this is almost like a tokamak. It's a toroidal device, but it's not axisymmetric. It's a little wiggly. On the left, you see the machine during the construction phase. Construction was completed about a year ago. German Chancellor was there for the opening. And there have been some simulations being carried out for this device. And what you see here is that the turbulent transport is not evenly distributed, but it comes in ribbons where it's stronger or not so strong. So here we are again making predictions that people in the next few years will be able to verify in experiments. And this together is just intended to give you the basic flavor of where we are right now, so we can actually do simulations that are realistic enough to give us the boldness to make such predictions and say, if you measure here and there, this is what you will see. And we are having quite a bit of success as a community worldwide. And this is my final slide. So these simulations have been matured significantly over the last maybe 15 years or so. And one key element in this progress has been the availability of high-performance computing. Again, always mixed with good algorithms and a lot of computer science and applied math. The experiment simulation comparisons have become routine. That's remarkable. When I started doing this like 25 years ago, it was unthinkable that you would do a simulation that would be actually compared with a measurement. So experiments would not seriously listen to you. You could maybe talk about qualitative features or you know, some large-scale effect. But you could definitely not say, you know, this is what you will measure if you do the measurements. That's my prediction. Now we are in a position to do this. That's big progress. But there are also still gaps in our understanding which come from this multiscale, multi-physics situation. We also have to extend our simulations from present-day machines to the future machines like ITER, which are in a somewhat different parameter regime. And these are all topics that are to be addressed and are being addressed in the context of this project here. Two topics have turned out to be frontier areas in our research area. One is the plasma boundary. Although its volume is relatively small, it turns out that most of the action when it comes to the success or failure in the future of fusion has to do with the behavior of the boundary. First of all, the boundary is largely responsible for the overall confinement of energy. That's a big point. The second one is that the boundary is in touch with the wall. As I said, this is bad for the plasma potentially. It's also potentially very bad for the materials. And if we can run the experiments in a way that the materials survive for sufficiently long times and the plasma is not cooled off too much via some stuff drifting in from the wall, those are questions that have a lot to do with the plasma boundary, and most of the success that we've had to date has to do with the plasma core. So, you know, when I say good comparisons between simulation and experiment, this is largely true for the core. It's much less true for the boundary. And there's lots of additional complications in this particular area of the plasma, and this will be a focus area for the years to come, I'm sure. A second one is materials. Because one of the key open issues in fusion research beyond the pure physics part, in the plasma physics part, is really the materials. The best choice for materials that surround the plasma. There are countless open questions, and we hope, in line with what we heard in previous talks today, that computational physics will be able to guide us in the right direction and you know, create some interesting options maybe in terms of the choice of materials. The overall vision of all of this is really fusion energy research driven by exascale computing. We think our application is perfect for the exascale era. We think we are within reach of computational resources that allow us to do pretty comprehensive and realistic simulations. And something that would basically be our dream of doing virtual fusion experiments for tokamaks and or stellarators, and then allow us to optimize machines and develop the optimum design of a future fusion power plant. Thank you very much.